like to introduce our keynote speaker, Professor Giancarlo Guizzardi from University of Twente. And he has been a great friend and a collaborator with us. This is the second year he's giving a keynote at ontoNexus. Like to welcome him, and he will be giving a talk, an interesting talk about the trustworthiness of system models. Professor Giancarlo, the floor is yours.
Thanks a lot, Margaret. Can you hear me?
We can hear you, yes.
Okay, so let me try to share my slides. Yes. Okay, started in the wrong. Can you see the slides well?
Yes, we can.
Okay, perfect. So thank you. Thanks a lot again for this kind invitation. This is I participated in the event last year and I like it very much. So I'm glad to be back here. Last year, I focused on this language called ontoML, which is based on this TLO called the Unified Foundation Ontology, and also the ecosystem of tools around ontoML. So today I'll do something different. So Maggot had asked me to focus on a number of things related to trustworthiness, in particular risk and security, but also how they connect to requirements engineering. So what I'm going to do is try to, in a short time, give you an idea of a number of things we've been building, both on the side of theories and on the side of languages and tools, in a network of ontologies in these related domains. So let's start with theories which are domain independent, so foundational theories that we use to build this more domain-specific theories. So we've been working in a group of collaborators for many years, for I think 25 years now, on this foundational ontology, this top-level ontology called the UFO, the Unified Foundation Ontology. And the UFO is a system, like most foundational ontologies, it's a formal system of formal micro-theories dealing with different aspects of reality. So a theory with finer-grained types, typology of types for classification and building of taxonomic structures, theories about higher-order types and multi-level modeling, about relations and relation or relationship reification, about occurrence, processes and events, parthood, dependence, roles, identity, and so on and so forth. And then this is, as I said, a system of micro theories that hang together and that we can prove certain formal, about which we can prove a number of formal properties. UFO is in this advanced process of standardization at ISO, so things are going really well, and we expect in a few months to have it as a new ISO standard. I would like to highlight, so I'll come back to this at the end, but I think there are a number of theories here, the ones I'm highlighting here, that I think it's what makes UFO distinct when compared to other TLOs, right? I agree. We had this discussion yesterday. There was a question from Maggot to Liza Kendall about the choice of TLOs, and she said something that to which I agree a lot. This idea that you have to look at what are the requirements of your class of applications in order to choose your TLO. I hope I will be able to convince you that for many domains in information systems, in social and legal domains, but also for in systems engineering, that you need theories for dealing exactly with that, with finer-grained distinctions among types, for dealing with higher order types and multi-level structures, for dealing with relations, domain relations, which are treated like objects, right? So they are reified, they have their own life cycle, they can have their own properties, they can participate in relations. and that we have a proper theory dealing with the full complexity of process and events. And I would claim that UFO has much more mature and much richer theories in all these respects compared to other ontologies. From these theories, we've been building a number of tools. As I said, last year, I focused on this modeling language called ontoML. And ontoML is, again, a language that has been designed to commit to UFO in three senses. The distinctions, the constructs in the language reflect the ontological distinctions put forth by the ontology. The grammar of the language is endowed with a number of grammatical constraints that reflect the axiomatization of the underlying ontology. And the actual primitives of the language are design patterns that represent these micro theories that constitute that ontology. So the language is actually a pattern language. And around ontoML, we have built a number of engineering tools, so methodological tools, catalogs of patterns and anti-patterns, computational tools for detecting, for building models according to these patterns, for detecting and rectifying anti-patterns, for generating code in several languages, including languages like OWL, for validating, for formal verification and validating the models via visual simulations, by a hack over Alloy, by also a number of complexity management tools for dealing with complexity of large models like viewpoint extraction, automatic modularization, and abstraction or summarization of models. Another example is constrained learning, so combining visual simulation, model finding with inductive logic programming for learning missing constraints and so on. So there are a number of tools around this language that we have been building for years. And then once we have this underlying theory, this TLO, which is reflected in the language and in the tools around this language, we can use this set of engineering tools to actually build ontologies in specific domains, so core and domain ontologies in several domains. So we have been doing this for years in many, many different domains. So for example, in this domains of the several subdomains of software engineering, we have built an entire network, an ontology network, a software engineering ontology network, dealing with things like requirements engineering, software testing, software quality, non-functional requirements, software configuration management, and so on. The focus today will be on another network in which we connect these notions of value, risk propagation, systems, security, and ethics, in particular, ethicality requirements for systems. Once we have these theories organized in an ontology network, again, we can build more engineering tools, domain-specific engineering tools, including domain-specific language, but also reference models and computational tools. So in this vertical axis here, what we have is a kind of ontological grounding, right? So we have ontologies in different levels of abstraction. So here, starting with the unified foundation ontology, I'll just give you the gist of a piece of this ontology, talking about events. For example, it's called the UFOB ontology of events. This ontology deals with participation of objects in events, mereology of events, how events relate to time, how events relate to each other in terms of temporal relations, how events bring about certain situations in the world and are activated, triggered by situations in the world, how events are manifestations of dispositions of certain objects interacting in a certain way, and how events can cause each other. So the idea of causation here defined in terms of these relations of between dispositions. Once we have something like this, then we can, for example, define an ontology of value and risk. So we've done this, a core ontology of value and risk. And on top of that, an ontology of security engineering. We have also defined ontologies, for example, about legal relations, UFOL, in which we define the semantics of different types of legal relations. And we have used this, for example, for defining the semantics of legal contracts, and ontologies about systems and system components and emergent behavior in systems and so on. The horizontal axis here would be this the move towards artifact design. So both at this domain independent level and at domain specific level, we can use this theories to systematically design different engineering tools, as I said, including different language, both. So we have an entire theory of ontology-based language design that in which we can use the ontology systematically to design abstract syntax, formal semantics, but also the concrete visual syntax of languages. So in the second part of the talk, what I'll do, as I said, is to go through the ontologies that are part of this network and to give you a gist of how these things are connected. So what is our theory of risk, of value, how they are connected? What is risk such that it can propagate, and how these theories of value and risk have been used to create an ontology of ethicality, of trying to explain the different dimensions of ethicality when applied to systems, and how it's being used to propose a methodology for eliciting ethicality requirements. And finally, I will say two things about security. So I will show how this ontology of security, again, grounded on the ontology of value and risk, has been used to evaluate de facto standards in cybersecurity, in particular the Defend ontology proposed by Maitri. And I will, by the end of the talk, show a more recent work in which we show that, a little semantics goes a long way, but it cannot get you further. So the need for having more substantial, more sophisticated ontologies in cybersecurity. I'll give you also a number of reference for, because this is going to be a short talk, so pointers to papers for people who are interested in any particular part of the talk. So this first one is this one called the Common Ontology of Value and Risk. And this paper shows that value and risk are very, very, they are basically the same phenomenon with a reverse polarity. They are strongly connected phenomenon. So here's, these are all built using this OntoML language. So here's a fragment of this model. So what this model is saying is that basically, so let me do this first. The gist here is the following. Value, according to this theory, is the degree to which certain capacities of an object, certain aspects of an object, can be enacted to manifest certain value experience, which are particular types of process or complex events that satisfy an agent's goals. So the value is the degree to which the intrinsic properties of the object can be enacted in terms of value experience that will satisfy an agent's goal. And this is what is modeled here in this fragment of the model. So you have value subjects which participate in certain value experience, and value objects as well, having a number of dispositions. So the value experience is a complex event composed of a number of sub-events, which are manifestations of the dispositions of this value object, but also certain value enablers, objects whose dispositions interact or enable the manifestations of the disposition of the value object. And these events will create certain outcomes that will satisfy the intentions of that value subject. So value is connected to risk, not only because in order to be at risk, something has to be of value. So risk is always the risk of the destruction of value, but also because the models are almost identical. They follow the same pattern, again, with a kind of reverse polarity. So if value is the degree to which certain intrinsic properties of the objects can be enacted to satisfy an agent's goals, risk is the degree to which certain vulnerabilities of the object interacting with the capacities and sometimes intentions of a threat entity can be manifested as risk experience, so events that can prevent the satisfaction of an agent's goals. And again, we have the same pattern here in this model. So you have a risk subject, which participates in a risk experience, which is a complex event in which an object at risk participates. This event will be the manifestation of the vulnerabilities of the object at risk, the vulnerabilities of certain objects, which are called risk enablers, and also the capacities and, again, sometimes the intentions of threat objects. So if these are intentional threats, and they can bring about certain situations that will dent the goals of the risk subject. Under this view, we can think of risk propagation in the following terms. So what does it mean for risk to propagate? We actually did an extensive study on this. And the semantics of risk propagation was, all over the place. So sometimes people are talking about belief updates in a Bayesian notion of propagation. Sometimes people are talking about just event chains, so causal chains of threat events. Sometimes people are talking about the impact of certain events on goals and how they propagate in a goal decomposition tree, right? Goals or intentions can be complex, so they can be decomposed in sub-goals. They can also bear influence relations to other goals, so they can make or break or hurt or help goals of other agents. By looking at that ontology, we can see that propagation here means these two things, means both the propagation of events, so the causal chain of events, and how the situations which are brought about these different events will impact the intentions of agents, of certain agents, the risk subjects at hand, and how this propagates across the relations within this between these intentions, right? So risk propagation is how the sequence of situations that are brought about by a causal chain of threat and loss events impacts the intentions of agents given the relations among these intentions. Now, once we had this theory of risk and risk propagation, we could actually develop a new a set of formal tools for dealing with this. So this paper just came up. What we did in this paper is to propose both a logics and a system of logics and a query language for calculating risk propagation scenarios and querying risk propagation scenarios. So what we did was to take formalisms which are used for safety, for example, in this case, fault trees, and formalisms which are used for security, attack trees, and create both a semantic integration and an extension of the combination of fault trees and attack trees. So here, for example, just to give you an idea, we can reason both with this propagation of events, but making reference to properties of the objects which are defined in the ontology, like the different phases of objects, like the door or the house or the lock, but also parts of objects. So, for example, we can reason with the neurological structures of the objects participating in these events that will explain the activation of other properties of the tree, of other nodes of the tree. And also with this participation relation between events, objects and events. And with these logics, we can define a number of properties over these graphs. We can calculate scenarios, and we can make a number of queries. So for example, here, given that an attacker destroys the door and that the fire does not break out, are any of the scenarios in which you reach the root node with a loss event possible? What are the events with loss events that can happen given that the lock is locked and the door is frail, and so on? So you can ask questions like this. You can assign probability for the causal transitions of certain events and calculate all this using these probabilities. Again, as we look at these models, we see that both value subjects and value enabler, also the value object, these are all roles, right? So the risk subject, the risk enabler, the object at risk, these are all role-like entities. Technically, they're called role mixing. So these are roles that can be played by things of different kinds. So in particular, being a risk enabler or being an object at risk, but also being a value object or value enabler, this is something which can be instantiated. So this role can be instantiated by a system. So here is a piece of an ontology of system that we've been working for quite some time. So this is a working collaboration led by Rodrigo Calhau in his PhD thesis and João Paulo Almeida, but in collaboration with all these nice people here. And this ontology will deal, again, with systems, with subsystems, with system components, with certain capabilities of systems and their parts, with the connections between systems and entities external to the system, but also the connection between components. And these connections, again, are types of objects which are objects in their own right. They are just existentially dependent objects, so objects which are existentially dependent on multiple objects, thus binding these objects, but they are themselves object-like entities that can go through phases, they can have parts, they can participate in events, they can play roles, they can change in time, maintaining their identity. So here the connection, the system connection, one particular subkind of system connection is an external connection between the system and an external entity. And this system connection can go through phases of being, for example, active or inactive. This ontology also, as this paper highlights, this ontology also deals with a lot of type level phenomena. So types, higher order types whose instances are types, are also part of the ontology itself. They are normal citizens of the ontology. And then, because we are able to deal with this type level structure, we can deal with things like specifying when you have an external connection between a component and an external entity, the component must be playing a certain role, and the entity externally must be playing a different role, and these two roles must be bonded in a certain way. Right? So you can specify at the type level the structure of the system, which is materialized by different configurations of components. Once we had this, again, this ontology of value and risk as well, one work that I'm quite excited about, that we have been working on for quite some time, but this was one of the papers that I think was published 2 years ago, with Renata Guizzardi, Glenda Amaral, and Joe Milopoulos. What we did in this paper was we wanted to address this problem of ethics of autonomous systems. And what happened was we were looking at the different standards for ethics and the different proposals. So, for example, there is a well-known EU proposal on how to address ethics in the systems. But as we look at these proposals, they are very abstract. So they prescribe a number of ethical dimensions and ethical norms, but there is a huge gap between those norms, very abstract norms, and the way systems engineers or requirements engineers would think about how to design certain properties of a system. So what we did in this paper is to use this ontology of value and risk to do basically the ontological unpacking, to provide an ontological explanation for these different dimensions of beneficence and non-maleficence and explicability and autonomy. And we didn't do that in the paper, but I can easily hint here at you how we can address even a notion of fairness in the systems. So just to, and another thing we do in this paper, by the way, is this paper is a materialization of a method we propose, which is called ontology-based requirements engineering, OBRE. And the whole method is it's grounded on this notion that we cannot derive requirements for phenomena that we don't fully understand. So it's very hard to have specific methodologies for security requirements without understanding what security is about, or trustworthiness, or ethicality. So the requirements engineering process should follow this process of an ontological analysis of the phenomenon or the domain at hand. And in this case, we are exemplifying this and materializing this for this domain of ethicality. So just to give you an idea of the models there. So here we have, I'm abstracting this notion of value and risk and just using a notion of prospect, but it's basically a variation of the pattern we saw before, right? So we have this notion of prospect ascription, which basically a set of belief or it's a mental attitude of a given prospect beholder, a value beholder or risk beholder, with respect to the prospect bearer, the object at risk or the value object. And this is done, this prospect description is done by matching, by comparing the intrinsic properties of the prospect bearer, capabilities or vulnerabilities, with the intentions of a given agent, the value subject or the risk subject. Now, once we can explain, for example, value or risk assessment, prospect assessment in terms of this systematic comparison of intrinsic properties of the entity and the goals of the agent, we can explain a number of these dimensions quite naturally. So, for example, beneficence is basically about enacting value experience, right? It's the system having certain properties that can be used to enact the manifestation of value experience or events that will satisfy the goals of a given agent. And non-maleficence is basically about the opposite. It's about preventing risk experience. Now, we can, grounded on these notions, actually prefer certain situations, certain value experiences over other value experience because of their relations to goals of these agents, right? So we can define preference relations of a given prospect beholder in terms of this prospect assessments, and we can use that to explain the deliberation process of a given agent, an agent that is acting in interaction with this prospect beholder. The decisions of this agent can be grounded on this preference relations. And then the result of a decision will be the formation of a new belief that will be manifest, that will trigger, will cause the occurrence of other actions. So in other words, we can go from prospect assessment, value risk assessment to preference, from preference to decision-making, and from decision-making to actions. And therefore, we can, let's say, run back the clock and explain actions in terms of decisions, which are explained in terms of preference, which are then explained in terms of these notions of value and risk assessment. So in a sense, there is a simple notion of explicability here, which is about reconstructing a path from the actions to decisions, to preference, to prospect assessment. Also, if we look here at this notion of preference, and here is preference over value or risk experience, as I mentioned before, right? Basically, there is a simple notion of fairness which can be defined here as well, which is fairness is assigning equal preference to bearers with equal prospect assessment, right? So a system would will have the same preference relation to two things which bring the same value and risks to the stakeholders at hand. Now, the missing dimension here is this dimension of autonomy. And what we did, as I mentioned before, we have proposed this UFO-based ontology of legal relations that we've used to analyze a number of legal texts, norms, but also to ground service contracts. In this paper, what we do is to define autonomy in terms of autonomy contracts. So these relations between systems, including autonomous systems working on behalf of a given stakeholder, are regulated by explicit contracts defined in terms of a number of social or legal positions, right? Dualities of rights and obligations, of permissions, of immunities, of disabilities, of powers to change the contract itself, and so on and so forth. And these are positions, these are properties that refer to action types, and they are either action types referring to an action or to an omission. So, for example, they are duties to do something or the duty to omit to do something. So there is a whole theory here on how to define these contracts. But again, this can only be done because these relations are reified relations with this kind of complexity. So here we have, again, autonomy defined in terms of explicit autonomy delegation contracts between an entity and an entity acting in a way that could affect its goals. So in a sense, we can define autonomy as having the full choices over actions performed by a system that will affect the goals of that given agent. Again, yes?
There is a question from Nicholas in the crowd here.
Am I running out of time?
Yeah, I think we are about the time, so we have time just for maybe you conclude and one question.
Okay, I'm going to conclude in 2 minutes.
Okay.
And then I'll get to your next question.
Sure.
Again, I just want to say that, for example, this external connection between a system and an external entity here could be specialized by autonomous contracts, by these autonomy contracts. Let me say, so I didn't have time to go through this. I'll just show you 2 other papers. One is in which we built an ontology of security on top of this this ontology of value and risk, and we have used to analyze and propose a number of changes to address problems in defense. And finally, this is a very recent paper in which we analyze current NLP systems for automating cyber threat reports. So we analyze many different systems, and here are the highlights. One is most systems use their own ontologies or their own private data, so it's very hard to compare them. Some of these are systems using traditional NLP technology. This traditional NLP technology surprisingly did better in all the experiments we did compared to more modern technology, like, for example, using Gen AI. The more modern technology relies basically on MITRE's attack ontology. And we show in this paper that there are still many ambiguous points there. So the leap, which is so the advancement which is required to have a major leap in this area of fully automating cyber threat reports, what is needed there is better ontologies, more expressive ontologies, more refined ontologies, and better data, and not NLP technology itself. Okay, if I have 30 seconds for takeaway message, very quickly. So ontology is very complex, so we have to manage complexity both horizontally, dealing with all these different levels of abstraction, but also building these networks. We have done this for many networks, but in particular for the scope of this talk, a network dealing with notions like value, risk, trust, capacity, resiliency, security, and so on. From this network, we have built a number of tools, including these formal tools. And again, a TLO that will support systems engineering, in my view, would have to deal with a very rich theory of types, including higher order types, a theory of relationship reification, and a proper theory of process and events. Thank you, and sorry for
Thank you so much for the inspiring talk. We can take a question from Nicholas.
A very inspiring presentation. Thank you very much, Giancarlo.
Thanks, Nick.
So when were describing the section about risk, I realized that there's a lot of things that we care about in autonomous systems, like robustness, observability, the assurance that ground can always get some information about what the autonomy system is doing as effectively facets of risk. Because effectively, the lack of robustness is the risk that there's some kind of failure events or certain kind of events that could cause the system to be unable to continue performing its function. So I could see that what you were presenting could be cast as a guideline for how to engineer better autonomous systems, in part with your point about if we can formalize, say, our concerns about assurance, reliability, observability, and so on in some kind of ontology, then we don't even know how to express and quantify and measure effectively whether subsystems exhibit those properties or not, just like what you do in this risk evaluation process.
I fully agree. So some of these notions that will pop up as non-functional requirements, they refer directly to vulnerabilities, right? And some of them, like, for example, robustness or resilience, for example, is actually a capacity to maintain another capacity under threat events, right? So again, you have to reason about what are the threat events and risk events and so on, right? For example, this ontology-based requirements engineering methodology highlights is that by understanding the nature of the phenomenon we are dealing with, we can use that to guide the process of elicitation itself, right? So, for example, when dealing with risk, we ask questions like this. So what are the possible vulnerabilities? What are the goals? What are the external threats? How can the capacities of these external entities interact with the vulnerabilities of the object itself? What are the events which can be their manifestations, in which situation, and so on and so forth, right? So yes, I fully agree. So that's exactly what we are doing, using the ontology to guide the process of requirements elicitation and elaboration and modeling, right? Because you reuse the patterns from the ontology itself to model these requirements.
Okay, perfect. Thank you so much, Giancarlo, for the great talk. We appreciate it.
My pleasure. I wish I were